We will now discuss the two main methods for transferring charge between objects. They are called conduction and induction. At the highest level, conduction just means you have two objects touching each other, physically touching. Induction, you will bring objects close to each other, and we will see how charge can be separated and transferred under those conditions. Before we can talk about conduction and induction, we need to define the concept of the ground. We've already shown how electrons can flow within objects, whether they are conductors or insulators. They can also flow between them. They can also flow from the Earth, which is an excellent conductor, to the objects, and from the objects to the Earth. Earth serves as the ultimate source and destination for electrons because of its huge size. The overall charge on the Earth is not going to be affected terribly by charges moving from small objects to it or in the other direction. Grounding will also be discussed further in the electric potential chapter of this course. When a conducting wire is attached between the Earth and another conductor, excess electrons will flow to the Earth, leaving the conductor neutral. This is called grounding. For example, if you have an object that has an excess number of electrons and it gets conducted to ground, those electrons will be attracted to the ground. They'll go back to the Earth, leaving the conductor neutral. Conversely, if you have net positive charge on an object, electrons will be attracted from the Earth. They will come up, they will balance out the charge, it will stay neutral. So, if you touch an object with a net negative charge, you may get a shock. This is because that conductor wants to get rid of its excess electrons. They will flow through you to the ground. If the conductor had an excess positive charge, the electrons would flow the opposite way, from the Earth through you to the conductor. In either case, there is a spark. You can notice this during the winter, especially when the air is pretty dry. If you shuffle your feet on a rug and build up a charge, and then you go ahead and touch a metal door handle, you'll see a little shock. You'll see a little blue, tiny lightning bolt, frankly. It's the same as lightning, just much smaller. That will be the charge going back to ground. When this concept first came out, grounding was actually called earthing because of the relationship to the charges going to and from the Earth, and in Europe sometimes you will see folks talking about earthing as opposed to grounding. It is the same topic. In the last slide, we showed how a buildup of electric charge on a door handle or on your person by scuffling your feet on the carpet in the wintertime can cause a small current to flow through you into the ground. That's annoying, hurts a little bit, but will cause no real damage. However, in the house we use objects that draw quite a bit of current and have a lot of electric charge that if there are frayed wires or a defect in the equipment could build up a large charge so that if you were to touch it, it would flow through you and cause great damage to you. So circuits and devices are usually grounded to protect them from accumulating that net charge that could shock you. To ground an electrical device, a conductor must be run from the device into the ground, giving a path to ground for the excess charge. Plugs for many electrical devices have a third grounding pin. You can see it up here, this little guy right here, that has a wire that conducts typically to a metal pipe in your basement, a plumbing pipe perhaps, that eventually has another wire going from it into the ground. This will enable any excess charge to flow through that wire into the ground instead of through you into the ground, which is a lot safer. Charging by conduction involves conductors that are insulated from the ground. They are touched and charge is transferred between them. We have here the insulator at the bottom. The whole point of this is to prevent any extra charge from going down, any electrons flowing down to the ground, or electrons coming up attracted by a net positive charge. The other convention that we'll have to get comfortable with here are these signs here. You can see we have 1, 2, 3, 4 positive charges, 1, 2, 3, 4, 5, 6, 7, 8 negative, so 4 minus 8 gives us a charge of negative 4Q. Over on this sphere, which we're calling neutral, you can see that there are 4 positive charges balanced by negative 4, gives you a net charge of 0. Now please don't confuse this with electrons. As you know from chemistry, Avogadro's number, there are 6.02 times 10 to the 23rd atoms per mole. So if this was aluminum, for example, and you had 27 grams of aluminum, That's a mole of aluminum, which means you have over 10 to the 23rd atoms of aluminum. Each atom of aluminum has 13 electrons. So you can see we're dealing with absolutely huge numbers of electrons. So that's not what this is. This is just to help us understand the concept. So in this case, you have a negative 4q over on this sphere, 0q here. The total charge between the two spheres is negative 4q. The spheres are now brought together and they touch. The electrons are now free to flow between the two charges, and the excess electrons from this sphere flow over to this one, and they are as far apart as possible as like charges repel. However, note that they were equally distributed between the two spheres. This one, 1, 2, 3, 4, 5, 6 negative charges. This sphere also has 6 negative charges. Note that the total charge that we started with on the two spheres stays the same. We still have a total charge of negative 4q. The spheres are now moved apart again. The charges that moved from this sphere over to that one are now stuck. They cannot escape. They are blocked from going to the ground by the insulator, and the air between them happens to be a very good insulator. So what we have now is, remember we had 6 negative charges on each one? So here we have 1, 2, 3, 4, 5, 6. So we have a negative 6q. We still have the 4 positive. 4 minus 2 gives us a total negative charge on this sphere of negative 2q. Same thing on this sphere. 6 negative charges are remaining. 4 positive, negative 2q. Once more notice that the total charge is the same thing we started with in the beginning. It's just divided differently between the two spheres. Now, on to charging by induction. This involves transferring charge between objects without them physically touching. The key piece we've added here is this ground wire. We still have the insulator, which protects this sphere from either losing electrons to the ground or electrons coming up, but we now have this ground wire, which is going to play a very significant part. The process will start by bringing a negatively charged rod. We could have used a positively charged rod, but in this case we'll use negative, and you can see how there are more negative charges than positive here. We will bring it near the sphere. What happens is the negative charges here will repel the negative charges in the sphere. They will build up on this side, and then since there is a ground wire here, these negative charges will flow down into the ground. Remember, the Earth is an ultimate sink for all electrons. They will flow down, and then we will be left behind with the positive charges here because, as we talked earlier, protons are not going anywhere. They're too heavy. They're locked in the middle of the atom. So we will be left with a positively charged sphere. While the negatively charged rod remains near the sphere, the ground is removed. That is key. The ground has to be removed while still in the presence of the negative rod. Now, note, there can be no more movement of electrons into the sphere. The insulator is protecting it from ground. We've opened up this connection so no electrons can flow there. They cannot jump the gap between the rod and the sphere or between the ground and the sphere. There's no jumping of electrons up here. Air is too good of an insulator. The rod is now removed. It is pulled away here. It is important to note that the charge on the rod is the same. No charge left the rod or entered the rod because it was still separated by an air gap between it and the sphere. However, the sphere lost electrons to the Earth, so it now has a net positive charge. So we now have a plus 4q, where originally we had 0. It picked up this charge from the Earth. However, compared to the amount of free electrons already in the Earth has gained an insignificant amount of charge. Charge is still conserved, of course, right? We have plus 4q here. Since we originally had 0, the Earth has now picked up a minus 4q. Please remember the order. The ground wire has to be disconnected first. Had we pulled the rod away first, the electrons that were pushed down into the Earth would have just rushed back up through the ground wire into the sphere, keeping it neutral. To summarize, Through physical contact, a charged object will transfer a portion of its charge to a neutral object. That is called conduction. Because of the conservation of charge, the amount of charge on the initially charged object will decrease. For example, we had the rod here. Let's say it had a charge of plus 4Q, and we had a sphere here with 0 charge on it. Not the best sphere, but you get the idea. After they touch, and then I pull them away, the rod will now have 2 plus, and the sphere will have the other 2 plus. You still have 4 positive charge, 4Q, but it's split between the two objects. The same thing would happen, of course, if this were negative charge. If these were 4 negatives, they touch, 2 negatives would be left behind on the sphere, and the rod would have 2 negatives also. However, the total charge remains the same as we had in the beginning. Induction has 2 major differences between it and conduction. Number 1, the objects are brought close to each other, but there is no physical touching. In addition, the neutral object will be grounded. It will have an electrical conducting path to ground. The charged object will repel similar charges on the neutral object to the ground. Thus, the neutral object will be left with a charge opposite to the initially charged object, whereas in conduction, the neutral object is left with a charge that is the same as the initially charged object. In induction, the initial object, such as the rod, will not lose any charge. The extra charge that shows up on the sphere, or the initially neutral object, comes from the ground. And as long as the ground is disconnected before the initial object, the rod, is removed, the neutral object will gain charge. Of course, if you leave the ground there and pull the rod away, the extra charge will flow either to or from the ground, and it will stay neutral. That's this point right here. If the ground were left in place, once the initially charged object was removed, the neutral object will pass its gain charge back to the ground. So the order in which you remove the rod or the ground is critical to making induction work.